Hello everyone, welcome back to my channel AKB Tutorials. I am Ashoke from AKB Tutorials. So we are discussing the important points of mechanical engineering in this channel. So various problems related to mechanical engineering which are important for the competitive exam as well as job interviews we are discussing here. So today we are going to see one of the most important problem related to simple stress strain, that is elongation of a bar due to its self weight. So in this there are three cases, so we will see the derivations of these three cases. Number one, deformation of a regular bar under its own weight. Second case is the deformation of a conical bar under its own weight. And third case, the deformation of a bar of varying cross sections. So now let us start today's session. So the first case, deformation of a bar of a regular cross section under its own weight. Okay, let us consider a bar. Say this is the bar is hanging from the top. The cross section of the bar is regular, means the cross section may be circular cross section, may be rectangular cross section, or it may be a square cross section, etc. So cross section throughout is same, that is regular cross section. No external load is acting over the bar. Now the length of the bar, say it is given as L is the length of the bar, and say cross sectional area is given by capital A. So cross sectional area of the bar is capital A and length of the bar is given by L, and the weight of the bar per unit length is given as small w. So thereby for this given bar, per unit length weight is small w. So total weight of the bar. So we can easily find what is the total weight of the bar. Total weight of the bar is given by, say it is capital W is equal to small w into L. So weight of the bar per unit length into length of the bar. So that will give you the total weight of the bar. Now we have to find what is the deformation produced due to its self weight, due to its own weight. No external load is acting over the bar. Now consider a section here at a distance x from the bottom end. So if we consider a section at a distance x from the bottom end and the thickness of the element is, let it is dx. Dx is the thickness of the element which is at a distance x from its bottom end. Okay. Now if we see the weight of this portion, means weight of the section, weight of this portion under the section, weight of this portion under this section will act as a weight on that particular section. So if we draw separately the section, say this is the section whose length is given as dx. Dx is the length. Cross-sectional area, say it is fixed here. And the cross-sectional area is capital A as given here. So cross-sectional area is capital A. Now this bottom portion will act as a weight on that section. What is the weight of this bottom portion? So if we find out weight of the section below, weight of the body, weight of the body below the cross section as we have considered is given by, per unit length it is small w into, for x length, so it will be wx, it may be in kg or in kilonewton or in newton, whatever may be. So w into x, so that will be the weight of this section, this portion of the body. So weight acting on the element is equal to w into x. So now this elemental area, what we have considered, the weight P is equal to w into x. Length of the section is dx. Cross sectional area is A. So the deformation produced for this element, the deformation produced in this element, is given by, so we know P into L by A into E, where E is the Young modulus of elasticity of the material of the bar. So here P is equal to W into X, small w into X. L is given by dx, and cross sectional area is considered as A, and say E is the Young modulus of material of the bar. So then the elemental deformation is given by Wx dx by A into E. Therefore, the total deformation produced in the bar, the total deformation produced in the bar is given by, if we integrate, so we will consider number of elements and we will find the deformation in all the elements, and if we add the deformation of all the elements, it will give the total deformation. That means we will find the total elongation produced in the bar by integrating this formula, that is W into X into dx divided by A into E from 0 to the length of the bar, 0 to L. So total deformation produced in the bar is given by integration 0 to L Wx into dx by A into E. Now you can see these are the constants. So it will come out, that is W by A into E integration of 0 to A x dx. So that will be x square by 2. So we can write W by A into E into x square by 2, and if we put the limits, that will be L square by 2. So W by A into L square by 2 will be the deformation produced in the bar, and also it can be written as small w into L into small l. So we are dividing this L square is equal to L into L by A into E into So 2 we are taking at first. Okay. 2AE is equal to, what is the value? What is this value? W into L is the capital W. So capital W into L by 2 into A into E. So this is the deformation produced in this bar. The bar is of regular cross section. Regular cross section means cross section may be circular, may be rectangular, may be square cross section, may be hollow cross section, but throughout the cross sectional area is same. For that bar, we can calculate very easily how much deformation is produced in the bar. So that is given by W into L by 2 into A into E. So that means what is W? That is the total weight of the bar which is hanging freely from top. L is the length of the bar, 2 into A into E. Okay, that is the first case. And we will see the second case, that is deformation of a bar of conical bar. Deformation of a conical bar under its own weight. Of a conical bar under its own weight. So this is the second case. So say conical bar is hanging freely from top. Say this is the conical bar is hanging freely from the top of the length of the bar is, say, L is the length of the bar, now considering an element at a distance x from the bottom, let this is the element we have considered for our derivation, which is at a distance x from the bottom, and the thickness of the element we are considering as dx. Okay, and let the cross sectional area at this point is given by capital A. So the conical bar is hanging freely from the top. We have to find out what is the deformation produced in the bar. That means what is the delta L, total deformation produced in the bar. So for that we have considered an element of dx thickness at a distance x from bottom of the bar. Total length of the bar is given as L, and let the cross sectional area at this point is capital A, and the element is considered at a distance x from the bottom, whose thickness is delta x, and the Young modulus of elasticity of the bar material, that it is A. So now I am drawing this element. So the elemental area is given as A, Young modulus of elasticity is E. Let this bar is fixed at the top, and the bottom portion will act as a weight of this bottom portion of the section will act as a weight. So let this is P. So we will find out what is the value of P, and the length of the element is dx. Dx is the length of the element. Now what is P value? P value means the weight of this bottom portion will act as a load on the element, this bottom portion. What is the weight of this element? See, we know that this is a conical portion. Now first we will find out the volume of the cone. Volume of the cone is given by volume of cone under the section is given by 1/3 into area of base, means this area into height. 1/3 area of base into height. So we have got the volume of the bar under the section. Now what is the weight of the bar? Volume into density, that will give the weight. Okay, volume into density into G. Okay, that will give you the. Okay, directly you can consider, let Wx is the weight density of the bar. Weight density of the bar. This will be given in the problem, or we can directly find the volume into rho into G. Volume into rho, that will give the mass into G, that will give the weight of the bar. So directly we can find, say this is the Wx. So Wx is given by volume into rho into G. Okay, so this is the weight of the bar. So 1/3 area into x, so that will give the volume into 1/3 area into x into Wx. Okay, so this is the weight of the bar, and we have denoted here by P. So we can write P is equal to 1/3 A into Wx into x, or directly just write, don't make a confusion. So W is the specific weight of the bar. So W is the specific weight of the bar. So we can write P is equal to 1/3 A into W into x, that is the weight acting on that particular section which is at a distance x from the bottom, whose length is given as dx, and cross sectional area is A, and Young modulus of elasticity is E. Therefore, so we know the elemental deformation. That means this bar will deform by some amount. So that is given by, say, delta L, which is at a distance x. So elemental deformation is given by delta L, which is at a distance x, is equal to, so we know the direct formula, P into L by A into E. Now we will put the value. So we have got the P value, that is 1/3 into A into W into x. What is the length of the element is dx divided by A, we have considered A into E, the Young modulus of elasticity. Now you can see the A will cancel out from this equation. So the elemental deformation is 1/3 W into x into dx divided by E. So W by 3E, these are the constants. So okay, so deformation, elemental deformation we have got. Now what is the total deformation of the bar? So we can write total deformation of the bar. Deformation of the bar is given by the integration of this elemental formula, that is 0 to L, this formula, that is 1 by 3E into W into x into dx. Okay, so that is given by W by 3E integration 0 to L x into dx, and that is equal to, so after integrating put the value of the limits, so it will give you W L square by 6e. So this is the total deformation of the bar, it is denoted by delta L. So delta L, total deformation of the bar, is given by W into L square divided by 6 of E, where W is equal to the weight density of the bar, L is the length of the bar, and 6E. 6 is a constant and E is the Young modulus of elasticity. So by this way we can easily calculate the total deformation produced in a bar, in a conical bar. Now we will see the third case, that is deformation of a bar of varying cross section. Now let us see the third case. In this, the deformation of a bar of varying cross section. So we have to determine what is the deformation produced in a bar of varying cross section. The bar varies, so in figure shows a bar of variable cross section. So at top the cross sectional area is A1, and at bottom, so if you see, the cross sectional area is A2. Length of the bar, this taper bar, say is L. Now consider an element of dx thickness at a distance x from the bottom. So we have considered an element, so let this is the element. What is the length of the element? So it is dx is the length of the element, and the weight of the bar under the section will act as a weight to the element. Now what is the weight of this portion? So this we will find out what is the weight of this portion of the bar. Okay, so let this is given by P. Now P is obtained by this formula. Weight of the bar under the section is given by integration 0 to x gamma into A into dx. So you can see A into dx, that is the volume into gamma means weight density of the bar. So that is the weight of the bar, and if we integrate from 0 to x, so 0 to x, so it will give the weight of the bar acting under the section, so gamma into A into dx. Now stress developed in the element. So in this element, what is the stress developed? That is the load. Load is given by this one P divided by the cross sectional area. Cross sectional area is taken as A. So gamma, so it is a constant term, it will come out. So gamma integration 0 to x A into dx by A. So that is the stress developed in the element. Now due to that there will be some deformation produced in the element, and the total deformation produced in the element is given by, total deformation produced in the bar is given by, so total deformation of the bar, it is given by 0 to L, that is from this point to this point, gamma integration of 0 to x A dx divided by A into E. This is the total deformation produced in this bar of varying cross section. So bar is a variable section bar. Due to its self weight, what will be the deformation produced in the bar? So we have to determine that. Now for this is the element. On the element, this bottom portion will act as a weight. So we have to consider what is the weight acting on the element, that is P. P is given by the weight from 0 to x, that is 0 to x, integration of 0 to x into that is gamma into A into dx. What is gamma? Gamma is the weight density of the bar material. A into dx is the volume. So if we integrate this will give the total weight under the section. Now due to this weight, some stress will develop in the element. What is the stress developed in the element is given by load by cross sectional area. Cross sectional area of the element is given as A, and so it will be gamma 0 to x A integration A dx by A. So this is the stress developed in the bar. Now that is element. Now deformation of the bar is given by 0 to L integration of this dx divided by A into E. That is the total deformation produced in the bar. Now we will see one question related to this topic. So questions are very simple. If you could derive the formula, then the solution of the problem is very easy. Now let us see question number 1. So we will solve only one question. So a steel wire of 8 mm diameter is used to lift a weight of 1.5 kilonewton at its lowest end. At its lowest end, the density of the wire material is 8000 kg per meter cube. Determine the elongation of the wire if the length of the wire is 100 meter, take E is equal to 205 gigapascal. So this is the problem. A steel wire of 8 mm diameter is used to lift a weight of 1.5 kilonewton at its lowest end. The density of the wire material is 8000 kg per meter cube. Now we have to find out the deformation or the total elongation of the wire. So initial length of the wire is 100 meter and take E is equal to 205 gigapascal. Now the data are D is equal to diameter of the wire is given as 8 millimeter. Length of the bar is given as L is equal to 100 meter. Then P is given as P is the load is given at 1.5 kilonewton, that is 1500 Newton, and density of the material of the wire is equal to 8000 kg per meter cube, and E is given as 205 gigapascal. Now weight of the wire. So first we will find out the weight of the wire. Weight of the wire. What is the weight of the wire? Is given by pi by 4 d square. What is d? D is 8 millimeter. So in meter it is 0.008 whole square. So pi by 4 d square. What is it? This is the cross sectional area into length. Length is equal to given as 100 meter. So pi by 4 d square into L into. So this becomes the volume. So volume into the weight density. What is given as 8000 kg per meter cube. So 8 into 9.81. So that becomes the specific weight. So 8 into, so we have to multiply G. So weight of the total weight of the wire is given by pi by 4 d square into L into the specific weight, that is that information is given 8000 kg per meter cube. From here we can find 8 into 9.81. Okay. So it gives 0.3945 Newton. So 0.3945 Newton is the weight of the wire. Now elongation of the wire takes place by this elongation of the wire will taken place due to the two reasons. One is some weight is acting at the bottom of the wire and due to its self weight. So now we will calculate the elongation of the wire due to elongation of the wire due to load which is acting at the bottom end. The load is given as, that is 1.5 kilonewton. Okay, so that formula is P into L by A into E. So what is that P value? P value is 1500 L in millimeter. It is 100 meter into 1000, that is in millimeter. Then pi by 4 into d square point, that is 8. Pi by 4 into 8 whole square, that is in millimeter, into what is E value? E value 205 into 10 to the power 9, that is Newton per meter square. So if we convert it to, so it will be 2 into or 205,000. So this one, what is that value? That is E value. E value is 205 gigapascal. So we'll see separately. E is equal to 205 gigapascal. Is equal to, we can write 205 into 10 to the power 9 Pascal, means Newton per meter square. Now if we convert it to millimeter square, Newton per millimeter square, so it will be 205 into 1000, 10 to the power 6, it will cancel out, so it will be this value. So 205,000. So it is coming, that is 14.56 millimeter. So the load is acting at the bottom of the wire. So due to that, the elongation produced in the wire is 14.56 millimeter. Now Now the deformation produced in the bar or the wire due to its self weight, that is elongation of the wire due to self weight is equal to, so we can write directly the formula and we will put the value of the parameters, that is WL square by 2E, WL square by 2E, as you have seen in the derivation part. So we have seen in the derivation, that is WL square by 2E is equal to, what is the W value? Small w, 8 into 9.81 into 10 to the power minus 6. Okay, so this is the W value into L, 100 into 10 to the power 3, that is in millimeter whole to the power square, divided by 2 into, that is E value 205 Pascal, that is equal to this one, that is Newton per millimeter square, 205,000 Newton per millimeter square. So after calculation, so it will give 1.91 millimeter. So let this is the wire is under load P, due to P the wire will extend, as well as due to the self weight also the wire will extend. Now because of the weight, what is the deformation produced in the wire? Is 14.56 millimeter, and because of self weight the deformation produced is 1.91 millimeter. Therefore total deformation in the wire, total deformation in the wire is given by 14.56 plus 1.91 is equal to 16.47 millimeter. Okay, I hope the idea is clear regarding this, that is elongation of a bar due to its self weight. Even the load, external load is not acting over the bar, then also there will be some deformation because of the self weight of the bar. Okay friends, that's all for today's video, and we will meet soon in the next video. Okay, thank you. We would continue further on this topic in the next session. Keep being connected with us and ask any question in the comment section. Like, share, subscribe, and don't forget to press the bell icon to get notified for future videos. Thank you and see you soon.